A recent study referenced by NIH described the ICU conditions at a hospital during the height of the current COVID-19 pandemic. Of the COVID patients taken into the ICU, 56% required mechanical ventilation. For non-invasive and invasive ventilation requiring patients, the mortality rate was a whopping 79 and 86%. Many COVID-19 ICU patients have an increased chance of developing acute respiratory distress syndrome, a lung injury with a high mortality, which requires use of a ventilator. The global pandemic brought attention to the shortage of efficient ventilators able to provide air to the abundance of patients in need. Hello, my name is Zaria Oliver, and I've spent my summer conducting research in the biorobotics laboratory here at Carnegie Mellon University. I did this under the leadership of Dr. Chaucet. I've been working on the RoboVent team where our goal is to create a portable, low-cost ventilator whose performance is comparable to those of the ICU. The ventilator combines mechanical and pneumatic design with robotic control to form a closed-loop system that can provide positive pressure, forcing air into the lungs and maintaining airway pressure through exhalation. Currently, the device hardware must be modified in order to adjust and test components, affecting parameters such as the volume of air being supplied or the speed of inhalation. In this project, I created a model for the RoboVent system which allows for parameter values to be tuned and assessed. I used MATLAB's Simulink graphical programming environment as a tool for modeling the system. I also spent my time this summer creating a model for a previously non-existent gas mixer subsystem located at the start of the system process. The Simulink environment consists of block tools that allow for elementary functions to be performed. To create these novel and more complicated models, I integrated these blocks to form a comprehensive model mirroring the RoboVent system. Just like the device, the model consists of an inspiratory section related to the ventilator patient's breaths in, and an expiratory section relating to breaths out. Key components of this model are the pressure and flow sensors, also the emergency breathing and check valves, and the emergency pressure check located along the ventilator route, which are subsystems with their own smaller models. The gas chamber is a subsystem that I specifically remodeled for Simulink representation, as the MATLAB environment did not have the tools necessary to do so. It provides the pressure of the gas mixture and allows for adjustment of the gas source flow rates, which affects inspiratory pressure and fraction of inspired oxygen. This work creates key parts of a model that provides ease in evaluation and alteration of parameters without modification of the device hardware. It also allows for a graphical model displaying pressure and flow rates at various locations of the path over time. Not only can these models simplify the RoboVent design process and its performance when in use, but they also add to the library of Simulink gas system models. Overall, this research brings us a step closer to ensuring efficient ventilators for future ARDS patients, and it strengthens our emergency preparedness for future global disease outbreaks. Thank you.